All right. Okay, Satya. Yeah. So your question. Oh, so, so it's a product? Yes. Okay. So 2 factorial times 4 factorial. And, ah, okay. Yeah. So, and this problem can possibly done in many ways, but since we are doing induction, let us see. So maybe Satya, if you have tried something, you could tell us. Hmm. So for n equal to 1. So can you tell me what will be the actual base case? What will be the numbers that we will have? Exactly. So, but n will be equal to 1. And because n, if you're doing induction on n is 1, but then the left hand side is 2 factorial. And so n is 1, so this side is 2 factorial to the power n is 1, so it holds. Okay, so base case is fine, right? So this is the base case. So now how should we go about, what should be the induction hypothesis? What should we assume? Yes, right. So we can just say, well, it's the same thing as above, but let's just write it. Okay? Assume. So we just assume that this. Sorry. Yeah, you could put n equal to n also, doesn't matter, but just a name. Good. So this is something that we assume is true. Okay. So now what should we do next? Exactly, right? So our task is, let's just write that. We just want to show the same thing for k plus 1. So that would become, let's keep the 2k factorial. And this here, it will become 2k plus 2. And just writing it factorial. And here we have right. So how do we show this given what we have assumed? Yes, exactly. So we just use it, right? Yeah. So using this thing, we can say that this thing is bigger than. So I'm just writing it below. This thing is bigger than. So just the straightforward use to begin with, and we'll see if this works. If it doesn't, then we'll have to do something different. This times this, yeah, because that's the extra thing. So now it is enough. It may not be true, but it is enough to show that this is bigger than this, right? So is that point clear? Right? So let's write this. Now, one should note that I am saying it is enough to show. It need not be true, okay? If it's not true, it doesn't mean the question is wrong, okay? But if it's true, then it means we are done, right? Yeah, so because you're putting an intermediate inequality and okay, so we want to show this. Yeah, so this is k plus 2 factor. I think now it's all about simplifying this inequality, some cancellations. Yeah. Because I think if we do some cancellations, then what we get finally will be just something simple, something obvious, maybe. So what do we cancel in this? What kind of things are common in both sides? Right. Yeah, exactly. Right. Yes. So we can cancel that. Right. So let's just, I'm just writing one more step. That's all. To the power k and this k plus 1 factorial, right? Now, as you're saying, we can just cancel this. Okay. And hopefully let's see what's remaining. We want to say 2k factorial, 2k plus 2 factorial is bigger than equal to k plus 2 to the power k plus 1. So this is an equivalent thing. Cancellation is an equivalent thing, right? You can go back. You can go back from there to the original thing. So finally, this is what we have to show. If we can show this, we are done. So that's what we need to finally show. So any ideas how we show that? So think about this. Satya, is the cancellation okay? Yeah, that's easy. All right. I'll just give the necessary things here. So how do we say this, that the last thing is true? Yes. Yes, exactly. So let's just write it formally to say that. Yes, that's exactly the thing. So this problem is just like that. You have to just keep simplifying. Okay. Always factorials have these good properties. Okay. So again, we can, right? And then the rest should be even more obvious. If it's true, then it should be even more obvious. Yes, right. That's so. Those are the two important things. Yes, yes, that's right. That's right. Exactly. Yeah. So there are k plus one terms, and each of them is bigger than k plus two. Right? So if just saying, I mean, it's done, but you can just say that like this, that 2k plus 2 is bigger than k plus 2, 2k plus 1 is bigger than k plus 2, and so on, and multiply them, and but it's all the same thing. Simple. Okay. So again, just if there are any questions, just say okay immediately. Yeah. So this is an example of a simple. This is a very simple application of induction. Okay, over time, we will see more interesting applications, and then I'll have some things to say. This is a very simple question. However, looking at this, some variations come to mind, which you guys should try for homework. That will be interesting. And also during the week, because there's a gap right between the classes. Okay, tomorrow we have a class, but after that, so you can just ask me questions if you get stuck at something and you feel like we should ask. And I mean, if you find it, if you that's fine. But if you I want to ask, just ask it over mail or something. Okay. So then, so that if it's stopping your progress, then just so that you keep progressing. Yeah? So so that's the thing is like if I'm asking this kind of question. So there is a very simple question. We would like to compare this n factorial with n by 2, n by 2 to the power n. Okay? So first of all, just to guess or whatever, few terms you check and you can tell which one is bigger. Sorry, you're saying n factorial is bigger. No, I'm just asking like which one do you think is bigger? Right? So not a proof, but just what you think, so that I can make the question because I don't remember. That's why I'm asking. Yes, Satya, did you get anything? Which one is bigger? Like maybe first few numbers. Okay, for n equal to 6, so my calculation may be wrong. So just check for n equal to 6 once. Because your first few numbers, things may be a little, but after that they, oh, wait, can you hear? And 3 to the power 6. So you see, and obviously no comment so far I can make, but you will see this kind of things in many places. That first few terms you will see some pattern, but then you would know that I should try more, and with experience you would know whether you should try more or not. That you will, but just that we have to be careful. So well, it seems like I'm not making a. It seems like this beyond a certain point, and that's what we are always interested in. First few terms one can just check with, so it doesn't not important. This seems to be true. And also these are very important inequalities. They're not just problems like fun induction application, but also they have more meaning to it. But first we'll just try to do this. Okay, you'll see if you can apply induction or induction doesn't work. It's up, you'll try and see. Okay? So this is the first question. There is another very interesting question which I just give me a minute. Just because otherwise, if I miss it, then not good. Just a 1 minute. Good. probably make it. So there is this book called Putnam and Beyond. So, sorry. So right now it may be a difficult book to follow. That's why I'm not suggesting it. But there was a very interesting problem. So just give me 1 minute, because this just came to my mind. So I think we should not miss it. Just 1 second. But yeah, you can follow this book if you want. This is. Sorry, I can't find it. It's in some other book maybe. Anyways, yeah, forget it. Don't want to waste time on this. So just try this one. This is a good question. Yeah. So that's as far as. So we have this factorial inequalities. Okay? Simple stuff. So you've noted down. Let's move on. So other questions? Yes. (2.7 to the power n). (3.5). Okay. Is divisible. For all n. Okay. But is this even a natural number? It is not. It cannot be. It's not a natural number. No, they probably, so they mean multiplication probably. I don't know. Yeah, they mean multiplication. Oh, no. Yes, they certainly mean. So even the question is, I've written it wrong. It's 7 to the power n, like this. Yeah. But since we have written, this is a very, this can also lead to this, and this in fact is, show that this is, so I'm saying that show that this is never an integer. We can forget the pipe for this. Show that this is never an integer. I mean, if it's not true, then you guys tell me. I can certainly say that it is an integer only for finitely many n, if it is so. Otherwise, it's almost never an integer. This is also a very interesting question. It's never an integer. Yeah, please try it from just, it's a fun question. Please note this down. These are interesting. This is because we are saying it's never an integer for any n. Induction may not work here, but anyways. Yeah. Okay, so now let's come to this divisible by 24. Okay? So yeah, please try these questions. This is an interesting question. So removing this, never an integer. Yeah. Okay, so so this is just looks ugly a little bit, but yeah. So we have been doing this divisibility kind of questions in the number theory class. So how do you approach such a question? Nagesh, so what have you tried? Okay. So let's quickly try this. Should not be very difficult. Let's try it the good old induction way only. Maybe it's no harm doing that without any congruence language also. So let's set it up. Base case. We'll not check base cases in most questions unless we feel there's something there. Okay. Base case we don't need to check. So, and also we won't say k and so on. That is for when you write it. Okay. But what we'll just say is we assume this. Okay. I mean, that's how you would do it anyways in your head or in the rough paper. Assume this, and we want to show that 24 divide, this is the symbol of 24 properly divides with no remainder, 24 divides this. Okay. Obviously, there's a language of congruences which we have developed. Maybe Satya, you don't know this, I don't know, but we will not be using that. And this technique also is this induction technique itself is sometimes independently useful when the congruence method doesn't work. Anyways, yeah, n+1. So now how do we, again, this thing is just we need to know how to jump from n to n+1, right? Somehow, like last time we did something, but here what should we do? That's all we need to. Yeah. So think about this. Take a time and think. Yes. Any ideas? We just need to know how do you go from n to n+1. That's the key thing. I'm just looking for that problem. And just meanwhile, but please tell me. Yeah. Yes. Yeah. Yes. Right. Just equate it to k. So let's just so we'll soon become informal like this while solving. Okay. So k or 24k or just k. Okay. Let's just say just k. Yes. Yeah. So it has to work like that, like if you do it like that, right? So just substitute that for 5. Okay. You could say assume k is divisible by 24, but I would just maybe put 24k, right? And just substitute that for 5. That's the easiest substitution. Yeah. So the 5 is equal to this. Yeah, if something is not legible, just tell me. 24k thing, and we would like to show this. Now this should be obvious. I mean, let's see. I mean, if it's not, we have to see. We have to prove this statement. So Satya, is it okay how we applied what we have assumed into this expression? Yeah. Okay, let me know if something is clear. No. Oh yes, that's what I thought. No, I cannot hear you. Can you hear us? Satya, Satya. Yes, yes. Yes. Okay, good. So then we just do the again. These are just actually regular applications of induction. So they are little, but one must do them. Okay. So that so we need to prove this, but then we can forget about this 24, right? The rest is divisible by 24 or not is what we will need. So now why is this divisible by 24? That is the challenge. So we have applied the induction, we have applied what we have assumed into what we need to prove. And now we need to show this is divisible by this expression is divisible by 24. Yeah. So does this look any easier than the original question? If yes or no? Yeah. Yeah, but this might this miss. We can make it work, I think. Yeah, but the question now is how do you show that this is divisible by 24? Like it doesn't seem any easier. Huh. Hmm. So the some kind of things because um, if one has to again prove this by induction, how would that look like? It's 7 plus 2 and so on. And we are again trying to substitute something. Hopefully that will be easier. Maybe not. Yeah. But let's try to manipulate this expression and see. So if you take like this 7 to the n, then you have 2 times 7 to the n. This doesn't look any so this will become like 7 to the n times 16. Yeah, if you have to do that. 3 times 5 to the n. Or you could, yeah, is that also 16? Wait, yes, no, what? 3 times 5, and then this is 5 to the n, right? And then there is this, yeah, that becomes 18, right? If you do that, then that becomes 18, right? Otherwise it is 6, and yeah, doesn't look very useful. Let's then quickly do something else. Yeah, let's try something else. This seems, I don't know, doesn't seem easy. I mean, one can do this problem in many ways, and induction is probably good in some cases, but this case, let's see. So what is the other way one can apply induction? So maybe other way one can think of is maybe taking this, because this leads to just saying a more massive simplification. Or maybe it does not. No, so it does not maybe, because there is a 7, extra 7 that one has to carry. I'm just writing it like that. And then I will, so it's just the same thing, okay? But just trying different things, okay? That is, I think, probably the most important thing. So 24K is not needed to be written, but we're just writing it. Then we have 5. Okay. And then we have this 7. Because this is a truth, and it's not very difficult to prove. We're just trying to write it expression in different ways so that the truth comes out as obvious. That's all. That's all we are doing. Just trying to write it in a different way and seeing. Okay. This, and let's see. So again, as I said, you can forget about this 24. Should be clear why you can forget about that. But then let's move on. So then we have this 21 times 5 to the n, okay, plus 35 minus 5 plus 3 times 5 to the n plus 1. So yeah, let's simplify everything and write. Okay, let's not think too much. Maybe in the sense that this is 15 and this is 30. Now what? So this is n, and this, okay. So note, okay, this is a much simpler thing to prove. I'm not saying it's obvious. That depends on, yeah, but this is much simpler to prove. Okay. Now, certainly if you again apply induction, you can do. To prove this, you can again apply induction. Is it okay? Yeah, not a good solution. I don't know if induction has a good solution. There should be. It's a problem in the book, but you can think, yeah. But I'll just say here again, if you want to do this purely by induction without using any number theory, all you are using is this property of natural numbers, right? That it's recursive and so on, right? That's all you are using without any number theory, properties of remainders and so on we are trying to do. So again, use induction. That's why the proof is not very illuminating. Sorry, 1 minute. Yeah. So if it is true, then it should come. So is this fine? Yeah, nothing. Yeah, but that's what it is. Or we could also just try to simplify this on spot in the sense that we can take -6 and we can take a 6, because the 24 we can again forget, right? Now you write this as the -6, you can forget the -6 again, right? And you can write this. So now the job is to show that 24 divides 5 to the n minus. Now this surely you can show by induction or certainly by other means also. Is this a correct statement? See, it's not even a correct statement, right? 6 into 5. No, but the way I'm writing it as 6 plus 24. Just taking modulo 24, right? So then is it right that it comes down to this? But I should not forget the 6. Yeah, because you can tell me why. Because the 6 will help, right? Right? The 6 helps. So certainly we shouldn't forget the 6. Okay. So we are down to this question. So what is this? I'm just squeezing things here. Okay. I'm just saying that focus here is that this basically reduces to 4 dividing, again, just, yeah, same thing, nothing, yeah, adding this. Surely you can prove this. 4 divides 5 to the n minus 1. Oh, yeah, when n equal to 1, it is true, but it is true for any n. And it's clear, right? Because in fact, so we did this last day. So my claim is that we have, I mean, you can do this by induction again, but you can do this by induction again. But what I'm trying to say is that instead of looking at this, we try to simplify it in the right way, right? Because the 24 to take it out and so on and so on. So then we came down to this. Okay? But then notice that we have this, and this is what we want to show, right? That 5 to the power n minus 1 is divisible by 5 minus 1. What did we show last time? We showed last time that if let's call it m. If m divides a minus b, then m divides any polynomial in a minus polynomial, any polynomial evaluated at a minus any polynomial evaluated at b. So for a special case, you can take up the polynomial to be x to the power n, right? And apply this thing, apply this fact that we proved last time. So what I'm trying to say is that this is part of something much more general. It's not a coincidence, right? It's part of something, part of a much bigger thing, right? So all I'm trying to say is that trying to show you how how this is something that we have done already. Okay? But this is not necessarily the way you need to see it. Okay? But m divides a minus b, then m divides pa minus pb. This we showed last time, right? At least for simple quadratic polynomials, it's true. So if you take any px equal to x to the n, then what do you get? Yeah, you get that m divides x to the, so x means at x you'll put a to the n minus b to the n, right? So m divides this, then m divides this, right? But then what can you take m? I mean, simply take m as a minus b, and then what do you get? You get this. I mean, just the simplest version of it is just take m equal to a minus b, right? And a minus b divides a to the power n minus b to the power n. A fact that is not surprising at all, right? It works for, and that again you can prove by induction. So n equal to 2, right? A square minus b square. You know that a minus b divides is a minus b divides it. aq minus b cube, you know the formula, and you know, so this fact is true. That's all this is. This is a much special case of it, right? It's a equal to 5 and b equal to 1. Sorry, is it right? It's a much special case, and that's where we kind of see a glimpse of how this theory of polynomials, right, viewing this kind of expression as part of a polynomial can reveal much more. I mean, to begin with, it is giving us this more general thing, but also there is much more hiding behind. Okay, much more factors, and what are the roots of that polynomial that can tell you, okay, 4 divides 5 to the power n minus 1, but does 16 divide? For which, obviously not for all n, but for which n does 16 divide? So you would want more specific information without making the case too specific, right? You want some more information whenever it's true. So those are the things, but for that one has to know a combination of little bit number theory and polynomials, because you can already see a glimpse of that. Okay? So that's the point. I mean, this is just the philosophy that when you see an expression, you try to see it as part of a general. When you see a expression in numbers, you try to see it as a part of some algebraic expression, so that you can view this thing as part of some more general thing, which can reveal more things, right? Seeing something as part of something bigger can reveal more things. That's the nature of what we want to do, right? Usually. So this is an easy fact. Yeah. Satya, the question you had asked me in the beginning, so was that from AOPS, the AOPS book? Oh, which book had I sent you? Oh, was it there? But it was not. Maybe. Yes. problem you asked me. Okay, I even forgot what problem you asked me. What was the question? You some inequality, right? Yeah. So you asked me some inequality. Is it there? I cannot find it here, but anyways, yeah. Okay, no problem. It will be there anyways. Yeah. Correct. Okay. So then, more questions. You see, so through these questions, we learn things and ask more questions from those questions. So no other questions are there. Yes, problem number 12, right? Let's try that. So, yeah. So we are doing standard exercises so far. Okay, soon we will be moving into problems, into more interesting stuff. But yeah. So this is problem number 12. We want to. This is a very interesting thing. That this thing which looks like a fraction, it's sort of the opposite of what we were just asking, right? There was some expression which we said is never an integer, but here we have an expression which is like a fraction, but it's always an integer, right? Is an integer. A very interesting thing. For all k in n. Wow. Such a thing even happen, right? So, have you tried this, Satya? Do you know of this problem? I don't know if I've sent. Anyways. Okay. Let's try this. This is an interesting question. This is always an integer. So this is a very nice thing, right? This is like again a polynomial, but the coefficients are not, you see the coefficients are not integers, but still it's always an integer for integer input, right? If you put an integer input, it gives an integer output, even though the coefficients are not integers. Yeah. Since we are in the induction chapter, we will just apply induction, right? Or even in general, you can just apply induction, try to apply induction. Because yeah, showing something is an integer, induction is not a bad thing, right? Showing that it's not an integer, maybe induction, you have to see how there has to be some pattern in which you have to spot a pattern in which it is not becoming an integer, why it's not becoming an integer, and show that. Then you can use induction. And if you show something is not an integer. But if you something an integer, maybe it's yeah. Again, base case, let's not check. So let's assume this. Let's just assume this. Yeah. So we will assume that this is an integer. So this is some m, right? And we will obviously not expand everything. That will be very horrible. I see one can obviously expand it and do it. You can apply, if you know, you can apply the binomial theorem. So this will be this cube minus k plus 1 by 105, and we want to show this integer. So again, we would just like to use this thing. That's all we are saying. But or do we have to do something better than that? Yeah, so that may help. And note that the denominators are very specific. The last one is a product of these three. Yeah. Okay, you can just write it and see. Just a minute. Just this 1 minute. Yeah, let's just do that. 105. So 105 is 15. Yeah, that's yeah. So meanwhile, if there are some interesting ideas, then tell me. Some other ideas, just tell me. So note that this question is all now taking the common denominator gives me an idea, right? Is you can again go by divisibility, right? You could try to show that this kind of expression is always divisible by, let's say to begin with 3. Not a bad way, right? Right? You could, if you can show that that numerator is always divisible by 3, always divisible by 5 and 7, then it's an integer. That seems like an ad hoc way to do the problem, but it's just there, right? Just a way, right? So this just branches into these 3, but let's write one of them. Just want to show, let's to begin with the simplest thing is the 3 divides this, but this is extremely simple, I think. 3 dividing this thing. Yeah, and how hard can it be, right? These 2 are just gone. They have 3, and you see that will be in the nature of this kind of thing, right? Most of the expressions will always go away. So it's easier than maybe we thought. And that 70 is just 1, right? 69 is divisible by 3, so you can just forget the 69. That's just 1. And then we just want to show this, right? And that is easy. Try to show, right? That kind of thing is always divisible by 3. So Nagesh, you would recognize this also. We have done this in the other ways, right? A to the power p minus a is always divisible by p. Okay? But you don't need to use it in this. You can, but this is a special case of that. But point is, this is easy. So again, use induction or whatever you want and show this. For any k, this happens. You can just do simple factorization. You get k plus 1, k minus 1. You show that one of these 3 has to be divisible by 3, right? Just like that. And dot dot dot. The other things are similar, right? Just so for 5 and for 7 also. Will not be difficult, because again, if you go for 5, you see 2 of the expressions vanish, showing that this is, sorry, not that one. This will always be there. You show this is divisible by 5. Again, that's not difficult. It's again becomes k to the 5 minus k, because again the 20 is gone. Yeah, again, this is easy to show. And Nagesh, again, you see that this is of that Fermat's little theorem thing, right? A to the power p minus a. But it's easy to show by factorization. We don't need to use anything like that. And similarly, the 7. Okay. So good. So the idea of Satya, I was not going for this, right? I was not thinking about this. But you see, this idea, once you write it like this, then it suddenly, oh, this is divisibility. We can. Okay. So just tell me. So we have not completely done it, and this will be the nature. We will not complete all the solutions, because yeah, you should try this and then you should ask. Okay? But this, just let me know what is happening. Is it okay? Or yeah, is it okay, Nagesh? Satya, is it fine? Is anything here which is not clear? All right, good. Okay. So yeah, this got done in some, maybe this was not what they intended. I don't know. We can, yeah, this is fine. Yeah. But in fact, this is a very interesting thing, right? That there is this expression. I mean, this is fine. This is special cases they are working out. But isn't it very interesting, right? That there is an expression that is always an integer, even though it has these things, the denominator, which are not integers, right? But it's always returning an integer output for integer input, right? That's a very nice thing. Isn't it, right? Can you give me another example of such a polynomial? I mean, don't just multiply this by something and tell me 2 times this, but some other example. Can you give me another example of such a polynomial? It could be a quadratic also. Okay? Come on. Some other example of this kind of polynomial, which takes an input integers and gives you output integer outputs, but its coefficients are not integers. That's a very, very, very interesting thing, I think. Yeah, if the problem is not, the question is not clear, just let me know. All these we will explore much more in the polynomials topic, maybe. Yeah, very interesting things. Huh? Any expression? Yeah, I'm looking for an expression, right? Any expression which, any polynomial expression which doesn't have integer coefficients, meaning the coefficients are not integers, there are fractions, but on integer inputs it gives integer outputs. Yeah, we're trying to think, I mean, is this the only such polynomial, or are there more, and what are all those polynomials, right? Like, obviously you can multiply this by 2, and that is again an expression in which the coefficients are not integers, and when you give integer inputs you get integer outputs. But I'm looking for something different. So any examples? So it's already there if you look at the previous problems, in fact, right? For example, just look at just this expression. It's always an integer. I mean, it's obvious because there's a simple factorization, so it's obvious. But this is always an integer. Yeah, it's not a. We all know this, right? It's always an integer. What is another example? Now you can give me a third example. Anyone? These are called. You can, if you want, you Google this and read this or see this. Integer valued polynomials. So you may not be able to follow a lot of it now, but I mean, you will be able to. Let's see, that depends on you, right? But integer valued polynomials. This is a very interesting topic. Yes, some of the squares formula, right? That's again another one, right? Let's write that actually. So this is another one. And in fact, I mean, as you would not be surprised, you can in fact extend this. Okay, not just by 2. That is easy. That will be not giving a new example really. You can make this 6, or let me write 3 factorial. This is also an integer. Not difficult. Right? If you don't know, try to show. This is homework then. This is always an integer for any n. Right? Yeah. Same kind of reasonings. This is always an integer. Now, in fact, again, this is not surprising. This, for any k, you can put k equal to 100, 99, then this will become 99. For any k, this, because I could write k there, then I would have to write k plus 1, but this is a traditional way in which it's written. And if you have done some combinatorics, you would recognize this, but that's not needed. First, just, I'm not asking you to prove this, but this is also an integer. But if you expand this, you'll get a strange polynomial, right? Which you would not recognize maybe. I don't know. If you recognize it's good. Right? You'll get if you just think about it, right? If you expand this, okay, this is little believable, right? I mean, product of k consecutive integers is divisible by k factorial. Fine. Okay. Fine. Maybe you could approach to try to prove this. Like the small cases we are able to prove. 2, 3, even 4 you can prove if you're right. K equal to 2, 3, 4. Try them, write them out, spend time on that. That's what you have to do. But just think, if this was expanded and given to you, you would have some strange coefficients, right? The coefficients, there will be some fractions, and so on. But then that would be an integer valued polynomial. Okay. So this polynomial so this is a polynomial in what? It's a polynomial in n. The k is a fixed thing, right? I mean, variable is n. Okay, so don't think about k as a variable. The variable is n. Okay, I am varying the k for the examples, but the variable is n. Like in this, the variable is n. So this is some k. K is some 100, 99, some number. Variable is n. These are the marvelous polynomials. It's very, very important polynomials in all kinds of things. Okay? Some special kinds of interpolations that people are looking for, integer valued things and approximating it by integer valued things, so on, keep coming up. Okay, integer valued polynomials. So what I have given is a few examples here of polynomials which give you integer outputs in integer inputs, but they themselves are not having integer coefficients. Okay, that's a good thing, right? So far, any questions? That's an interesting question. That's an interesting question. Yeah, that's right. So that's also something that we should note down. I don't know the answer. So let's think. Let's actually try that now. Let's try it now. So we'll just write the problem. Yeah, because there is certainly something. Yeah, I would put 11. I don't know about 9. Might be true for 9 also. Oh no, sorry. Yeah, it can be true for 9 also. So 9. 7. I mean, if it's not true, then we would know. We will just check it. And if it's true, then but there is a 2 here. I don't know what this 2 is there for. Right? I mean, see, you understand, right? This 2 can bring up something there again, right? And the pattern could demand that you put some other coefficient there. So I don't know. This may not be true, but there is a very nice way to check it, which let's not discuss now. But there is a nice way to check it. But let's see. Is this an integer? No, so that's wrong. The last thing is wrong. So really, again, the question is, what should we take here? Should we take the LCM? If you're going to do that, yeah. Or I don't know if they meant LCM or, because there are several ways to generalize, right? It, in the sense that that's also a natural way to generalize, right? Like taking the LCM of those numbers. So I don't know if that's what you're looking for, if that is what they want. And I don't understand that too also. Right. So then what is the way to prove that this is not 9? Yeah. So then if you again take the LCM and so on, right, you would be left with trying to prove this, that k to the 9 minus k is divisible by 9. Again, is not surprising, right? Just take the LCM and see, that's what you kind of get. Right? Or no, so this is not correct. In fact, I will try to change. So let's just take the LCM. Well, it may not be, that was wrong actually, maybe. So we have this. So 1 minute. So what is the, just please take the LCM. Can you take the LCM? Okay. Yeah, so it's 7, and then you have to multiply with something, but it will have a yeah, the 135. Yeah, so just tell me what's the final expression that we get when you do this 7 5 30. So it's just 35 into 9 is the LCM, right? And for the 45 4 27 4 31 315 is the LCM. Is that right? And right, and so then when you take it, then you get 35, and you see the other terms, this k to the 7, this k to the 5, and this 2k cube, these will all have 3's attached with them, right? That's clear, because yeah. And then wait, no, but how can the LCM, oh my god, why am I doing these mistakes? But no, the LCM is incorrect. We have to take the LCM with 945. So the LCM is 945, right? Sorry. It's 945 is already there. So the LCM is 945. Sorry. So you have 945. And so then what is this? This is k times 105. Is that right? 105. And the last one is just k, right? And the other things are multiples of 3. So we can just ignore that for the time being, or they are multiples of 9, in fact, right? So we can ignore them. Yeah. And so we would be wanting to show that this thing, I mean, if this problem, if this is an integer, then this must be true, right? That 9 divides this, must be. If it doesn't, then the problem is, then it's not an integer, certainly, right? That's true. That's certain, right? Does 9 divide this? Can you give me a k for which 9 does not divide? K equal to 1. Right? 9 doesn't divide, I think. Right? But this is not true. We take all the numbers, right? Because we have to just clear the denominator. Because 945 is already there as a product, right? Or more than, yeah, it's a product. So already that's a LCM, right? Okay. So you get this kind of thing, 105 times k to the 9. Yeah. Whatever. And then you get this k. This is not divisible by 9. Certainly not divisible by 9. So the question is not true. That this is not an integer. So this doesn't generalize in the way we thought. Might generalize in some other way, but I don't. Yeah, that's yeah, that is there. But that's a very open-ended question. In what way does it generalize? So maybe one can try with 11, but I don't think that that prime kind of pattern. No, let's actually try. But the 2 is there. That's what I don't understand. That what is the 2 there for? So I'm a little hesitant. Okay, that's why. Because yeah, there's no pattern in that sense. Yeah. So but it's clear, right, that we have refuted that this is divisible by, just if that has to be clear first, right? Because if this was an integer, then this would be an integer, but the 9 would divide this rest of this, this from minus this minus this, and but it doesn't, so it's not an integer. So that's fine. But here, but we will soon see that there is a good way to check whether these expressions, even algorithmically, that's a actually very interesting thing, is that there is a very constructive way to know if given a, that's a very interesting thing. Given a polynomial, there is a very simple way to know if that takes input integers and gives you output integers without checking for too many inputs. So you have to just check for n input integers. If there's a 9-degree polynomial, then I can, what I'm saying is, you have to only check this for 9 input integers, and you would know after checking for those 9 input integers, you have to choose them. Do you have to choose them strategically? Yes, you have to choose some, you have to choose them strategically. Well, in the end, it's not really strategic, but the proof is strategic. So my point is that, look, if you have this 9-degree polynomial that you were looking at, right? I'm saying that there is a very easy test that one can do. Some 9 integers are there, which one can check, in a sense that you take those 9 integers, you substitute them in the polynomial. If you do get integer output for integer input, then you can say that for all integer inputs, you'll get integer outputs. That is a very interesting result. Okay? But for that, we will have to explore more about how these polynomials are built. What makes up this kind of polynomials? What's the basis for these polynomials? But those questions have to be answered slowly. But many variants of those questions occur in all sorts of competitive exams and things like that. Okay, so we will see a few of them first later when we do. But we need to know a bit of polynomial theory. But a little flavor of that can be given maybe right now. Yes, any questions? Uh-huh. Yes, yes. That's why I'm saying that it's a very easy test. Okay, so in the end, the algorithm that you get is a very easy one, but there is a lot of there is some math that is there before that, which one has to use to conclude that that algorithm will work. Okay? And some very interesting and elegant maths in the sense, yeah, some interesting ideas are there, but I have discussed them in some other places, and obviously they are there. It's not my own anything by any means, but I was just taking a class on that maybe last month. I had taken this that was under the name of interpolation. There's Lagrange interpolation, and then basically interpolating using combinatorial, I should say, polynomials. But anyways, yeah. But that we will for later. Those are important topics. But just to say, just to give a flavor of that. Okay? And what is the general thing here? How are these special polynomials built? Some insight into that, we'll be happy, right? How are these special polynomials built? Keeping in the context of what we are, our exams and so on, right? Simple things. So we can look at this. And then my question is, can you write this polynomial in terms of, can you write this in terms of this and this? You will get some, in terms means with some coefficients, right? So some coefficient, and can you write it using, so these are like the blocks. These are like the canonical natural examples of these polynomials which give you integer outputs. I'm not saying that this one is not a natural example, but just, there is a certain sequence to the other ones that I've said, right? So, I mean, anyways, yeah. The point here is that now, can you use these two polynomials? I don't know. Can we use these two polynomials to write? So can you give me some coefficients using which you can, can do it? Well, it will not be difficult. I mean, if it's possible, it will not be difficult. Simply just cancel this, right? Because we want this to be true for all n, so we can certainly cancel, right? And so then all I'm asking for is something very simple, is find some integer here, right? Such that, and find some, okay, not, I don't know if it's integer, so that this is true. Okay, I'm trying to write this expression using these other two, which I'm kind of saying that are the building blocks. So can we just quickly find those two integers? Let's say x and y. Yeah. So just cancel this 2, 2, 6. This will become 3, 3, 3, right? Yeah. Then we get 6n plus 3 equal to 3x plus yn plus 2y. Yeah, so what should the x and the y be? Just because it's true for all n, right? Just put n equal to 3, 4, whatever you want, and find the x and y, right? So just try to find, just tell me what the x and y should be. Okay, maybe don't put 0 and 1, 0 and minus 1. Sorry. 1 and 2. Okay, wonderful. 1 and 2. That's the best that we could ask for, right? So what we get in the end, and one can just solve that. Okay, that's easy. You will, and if you get 1 and 2, then you get 1 and 2. You can't get something else, right? Because that is okay. That's another interesting question. But yeah, whatever. This is okay for us. It's just with 1 and 2. The point is that this times 2 times this is this. That is what I'm trying to say, that if you look at this particular integer valued polynomial, you are able to write it as a combination of these other two integer valued polynomials, which is already an interesting thing. It's already an interesting thing that you're able to write it as just a numerical combination. Okay, but also that these are integers. The weights that you're using are integers. This is something very nice. Okay, so there are two things which are there, right? That any integer valued expression that takes an integer and gives you out an integer. Yeah, if its degree is 3, then you can use these two polynomials and write it. And if its degree is 4, then you would just take the third one also, right? N times n plus 1, n plus 2, n plus 3 times by 4 factorial, right? And using those three, you can write that 4-degree expression which takes integers and gives you out integers. And similarly, 5-degree, 6-degree. That's what we think should be true. But also that you need not use any other weights than just integers. This is a very interesting thing that has happened, that is there, right? See, certainly, I mean, if I tell you that this takes in integers and gives you out integers, this one n times n plus 1 n plus 2 by 3 factorial takes in integers, gives you out integers, then you take 100 times that and 2 whatever 99 or whatever times the other one, and you add them, certainly you will get integers. But we are saying that any polynomial that takes in integers and gives you out integers is like that. That is the thing that's one thing that you would like to know, is it true or not? And for that, you have to just take take the sum of the good way to manufacture these kind of polynomials other than these standard examples. I take the sum of the cubes of the first n natural numbers, right? N times n plus 1 by 2 square, and try to write it as a sum of, and see if you get integer weights, and see if you can write and see if you get integer weights. So that's the problem that we can end with. Oh God, it's very late today. Sorry. So I'll just finish, just tell you this, what you try. So first thing is, if you don't know, then you try this by induction maybe, or suggest you try other methods also. Just look at, try it, just ask or try whatever. This is a standard formula. Yeah. But at least prove it in some way first. And then, so this again will take in integers and give you odd integers, right? N is a variable. Okay, n is a variable. Okay. Now what would you try to do? Yeah, if you're just curious, what would you do? You would say, well, no, I will just try to use this and find a weight, and use this. Very interesting thing. And then use this 4 factorial and find the weights. If I can find some weights, I'll be happy. And if I know that and if I get that they're integer weights, I'll be even happier. So solve this problem and see what weights you get. Okay. And they will find good ways to do these things and then prove some interesting things when we do polynomials. Okay. So that is where we will stop. Okay. Tomorrow we will begin with a little bit of polynomials and try to see connection with these kind of things. But we'll do some standard things about polynomials. We'll see that later. So meanwhile, about more problems, just see. Yeah, you can just brilliant and so on. I will send a problem set just to make things organized from other source, and then we'll discuss it next time. But just try as many different kinds of problems as you can, and yeah. So that's it for today. Usually we just keep it on time. I don't know. I just lost track of the time. Yeah. Okay. All right. So note this question down. If there are any questions, please ask me. If there are any questions about today, just ask me. Otherwise, then we are done. Yeah. Thank you. Thank you.